Okay, so in this FRQ, this is an example of a long FRQ. If you guys take a look at it, there are many parts to this. And so this is an example of what you'll see on the AP test. I think there are 2 of these on the AP test. Hey guys, when I'm lecturing, gotta keep it down. Thank you. Okay, and so let's go over the premise. Okay, so basically what this is telling us is that a student gets a chunk of metal and it's an alloy. So it's made out of copper and it's made out of silver. Okay, and basically students looking for the mass percent of silver. So what's the percentage of silver inside of the original alloy? That's kind of the scenario. Okay, and the way that the student is going to do it is the student is going to put it in nitric acid. So it's going to dissolve it. So it's going to dissolve it in nitric acid. And then after that, they're just going to precipitate the silver as AgCl. So basically, they're going to put it in a beaker or something. They're going to put the metal in there, the alloy in there. It's going to dissolve into ions. And then after that, they're going to precipitate it as AgCl. And that's going to allow the student to find the mass percent of silver. That's kind of the general premise. They're basically telling you what's generally going to happen in the lab. Does that part make sense? Okay. So what the student has to do first is prepare 50 milliliters of a 6 molar HNO3 nitric acid solution. Okay. Now, this is where the part A comes in. So the student is provided with a stock solution of 16 molar nitric acid. And then you got a bunch of different equipment. Okay. First thing we want to do is we want to calculate the volume of 16 molar nitric acid needed to prepare 50 mils of 6 molar. So you're trying to take a 16 molar nitric acid solution and turn it into a diluted or weaker solution. Okay. So if you guys remember, the dilution formula is M1V1 equals M2V2. So super simple. Doesn't matter which side you use first. Let's do M1 for our stock. And then for our final diluted solution, we'll do M2. But if you switched it around, totally fine. The math will be exactly the same. Okay. So M1, what is the molarity of our stock solution? 16, yeah, 16 molarity. Okay. We are looking for how much of the stock solution we need. So the volume of the stock solution. That is going to be equal to, what's the concentration we want to turn it into? Yeah, 6 molarity. And we want to create 50 milliliters of the diluted solution. Okay, so from here, pretty easy problem, right? The key was just figuring out that this is a dilution problem. Okay, so if you haven't done so, I will give you guys 45 seconds to punch this into your calculator. What's up?
So when I see molarity, what if I use the molarity equation to get the moles?
That's totally fine too.
Does that always work too?
Yes. Mm-hmm. Okay, so you should do 6 times 15. Oh, not 15, 50 on the right side, divided by 16. And you should get a final answer of 18.75 milliliters. Okay. All good? Okay, so key thing to note is that if we want to conceptually understand what's happening, you got your 16 molarity stock solution. What you're going to do is you're going to take out 18.75 milliliters of that. You're going to have another container. The final volume here is going to be 50 milliliters. And you're going to basically put in 18.75 mils of your stock and then fill it up with water till you hit 50. Okay, that's basically how the dilution works. All right. Yes. What'd you get?
0.05.
You might have forgotten to do a step. So on the right side right here, you should do 6 times 50.
I did.
Okay, 300. Okay, and then you're going to divide by 16.
Oh, so
Yeah, because you're trying to isolate the B1. Yeah, no worries. Of course. Okay, so that's going to be our volume. So make sure you like box it or have it somewhere where you can see it well, because we will be referring back to this as we go through the problem. Okay, so these long FRQs, as you guys probably have seen through our previous exams, they kind of build on top of each other. And so it's good to have our information organized so we can go back to it. Okay. All right, let's go to part 2 now. So part 2, briefly list the steps of an appropriate and safe procedure for preparing this. So basically, now that we did the math, we know how much stock solution we need. We're going to write a procedure that tells us what is a safe and effective way of making this solution. So you have to use these materials up here. And so I'm going to give you guys, actually, let's just go through it together because this is kind of easy. Okay, so because they talk about safety, and since they give you safety materials, we got to list that equipment, right? So you can just say something like, you want to wear your safety goggles and gloves. Okay, it's the first thing you want to do. Something like that. If they list the equipment like this super specifically, you're going to want to list them specifically. Yeah. So just again, assume that I am your grader and I'm a jerk, and I'm going to try to take away as many points as I can. So try to be as specific as possible without writing an essay, because I'll take off points for that too. Okay. All right. So next thing we want to do is since we're going to be taking out, remember we just calculated that the volume of the stock that we need is 18.75 milliliters, right? Okay, so we want to create our diluted solution now. And so what we can do is we're going to want to measure out. So we're going to measure the volume that we need, 18.75 milliliters of stock solution. If you want to be more specific and write 16 molarity, you can do that as well. Okay, H9O3. Okay, and then if you take a look at the what is it? The equipment that's given to us, we use these two. Which equipment should we use to measure out the stock solution? Okay, so the dropper is how we transfer it, but how are we actually going to measure the stock solution that we're using? Not the beaker, the cylinder. Yeah, so the cylinder is used for measuring exact thing. Beakers are more kind of like estimating, so it's more like a container where we mix it after we measure it. Okay, so we're going to measure it in a graduated cylinder. Okay, you want to write that it's 100 mil, that works too. All right, now one thing I do want to mention before we move on is that if you guys notice, or if you got, Nick, can you bring me one of those graduate cylinders or two of those?
Yeah.
So I'm gonna pass around 50 mil graduated cylinders, and you guys can take a look at the measurement. Yeah, on the rack. No, turn around, walk straight on your right. Yeah, yellow base. Okay, if you can grab, are they hundreds?
Yeah.
Okay, yeah. Can you grab like 2 or 3 of them and then pass it back? They're clean, guys. There's nothing in there. Yeah, and then just pass it down the rows for them so they can take a look at it. So if you guys take a look at your graduated, if you take a look at 100 milliliters graduated cylinders, okay? Yeah, just give it to one from that row, one from that row. And you guys can take a look at it and pass it down. But as you guys are looking at, just wherever, maybe in the middle. Yeah. So if you guys take a look at these cylinders, let me ask you a question as you're looking. Can you measure 18.75 accurately on there? No, right? If you look at the marking, so after you look at it, pass it down so everyone can take a look at it. What are the increments for the measurements?
1.
Yeah, 1 milliliter. So we can only measure with the accuracy of 1 milliliter, right? And so we want to change this number up so that we can have a more accurate reading. So what should we change this to? Yeah, 19. Okay, so we're going to change it to 19 milliliters. Okay, so just keep that in mind. The increments are just 1. And so, yeah, we can't measure 18.75 exactly. So we're going to want to get it to 19. Okay. Yeah, so you're going to want to round up. Okay, based on the increments. Okay. Make sense? Okay. So we're going to measure out 19 milliliters, so 18.75 milliliters of your stock solution in a 100 milliliter graduated cylinder. Okay. All right. Next, what we're going to do is, remember, we said we're going to take the stock and transfer it into a beaker. And so what we're going to do is we're going to transfer your 19 milliliters of stock solution into your beaker, 100 milliliter beaker. Actually, I'm really sorry, guys. I forgot something. This is not the next step. It's going to be a step later, so just keep that there. I'll number it differently. I'm sorry. Okay. Okay, so before we do that, what we're going to do is we're going to measure out our water now, right? Because we need to dilute it with water. How much water should we use? Yeah, 50 minus 19, right? Because, yeah, we want to do 50 minus 19 because our diluted solution has to be 50 milliliters. But since we have 19 milliliters of acid, we want the difference to be our water. So that's going to be 31 milliliters. Okay, so what we're going to do now is same thing in the other graduated cylinder. We're going to measure 31 milliliters of distilled water in a 100 milliliter graduate. And I'm going to write GC. For our notes, you can write GC, but on the test, please write graduate cylinder so there's no confusion. Graduate cylinder. Yeah. Yeah, if it's confusing to you, just write out the whole thing. Yeah. All right, so far so good. I know this procedure stuff is pretty dry, okay? All right, so what we're gonna do now is we're going to transfer the 31 milliliters of distilled water into the 100 milliliter beaker. Now, the key thing that I want you guys to keep in mind, and the one that I gave to you prematurely, number 5, that's gonna be number 5. And the key thing that you guys want to make sure you guys know is you're gonna always add acid to water. Okay, so you want your water in there first, and you want to add the acid later. Okay. Yes. It's safer that way. This is a safety rule. Okay, because if you add water to acid, what you're doing is you're basically diluting the acid rapidly. And so if you're doing that, that causes more bubbles and heat and things like that. Whereas if you add the acid slowly to water, you're more slowly increasing the molarity of the water or the acidity of the water. So this is an important safety rule to keep in mind. So you always add acid to water. Okay. And then the last step, you're going to stir with stirring. Okay. That's good. We didn't talk about the dropper too much. So you guys don't need it's not that important in it. And I'm looking at the answer key right now, and they don't talk about the dropper as well. So if you want to talk about the dropper, you can, but you don't have to. Okay. Yeah, so yeah, you got to have all 6 of these steps in there. The dropper would go when you're transferring it into the graduated cylinder. So use dropper for final milliliters. Yeah, that's where it would be. It's interesting it's not on the answer key, but okay, so those are the procedures. I know, very dry, right? It's not as fun as the math part. Let's have too much fun in this class. Alrighty, you guys ready to move on? Okay, let's move on to number 3 now. So why is it not necessary to use a volumetric flask to perform this dilution? I'm just gonna give you guys the answer. So volumetric flasks are those ones that are round on the bottom and they have that line. Do you guys remember we used it for solutions, making the solutions? Okay. So what we're gonna do, what you do with that is it tells you precisely what the volume of that container is and the solution is. So the reason why we don't need to use graduated cylinders, okay, is because how much how much stock solution do we need? Yeah, we needed 19. Okay, we needed about around 19 milliliters of HNO3, right? It was 18.75, rounded up to 19. Okay. And then we can say something like graduate cylinders provide two significant figures. Okay. And that makes a volumetric flask unnecessary. Something like that. Yes.
We mentioned that we rounded up to the next number for just the actual solution.
You don't have to. You can just write that we just needed two significant figures. That's fine. Yeah. Yeah, the amount of non-zero like numbers. Yeah. There is a section in the reading from way back when. But it's not that important. Yeah.
It's not that important.
It's not that important. Yeah. So you don't have to write it again exactly the way that I wrote it. The important things, the important points are that the graduated cylinders are sufficient for the margin of error that we're working with. As long as you hit that point somewhat, you can use different language. You don't have to mention the significant figures. That's totally fine.
What do you do this? How they similar question based on how to memorize what each item does?
Yeah, you're gonna have to know what the items do, but it's like stuff that's pretty simple. It's like graduate cylinders, beakers. They're not gonna ask for like super like niche equipment. Hello, Mr. Osclas. Good. You? Mm-hmm. Mm-hmm. Yeah, I mean, if she wants to drop in and check, I didn't see it, but if she might know specifically where it is. Yeah, of course. All right, sorry about that, guys. All right, we good with this one? You ready to move on? Yes? No? Maybe? Okay, we're gonna move on. All right, next thing we're gonna look at is another lab thing. Okay, so during the preparation of the solution, the student is gonna spill 1 ml of the stock solution. That is very, very strong. Okay, that will eat through your tissue. Okay, on the bench top. Okay, there are 3 bottles containing liquids near the spill. Bottle of distilled water, 5% NaHCO3, and a bottle of saturated salts. Okay, which liquid is best in cleaning up the spill? Okay. All right, so what we're going to look at now is basically if you react, basically you spill HNO3, okay, and these are the 3 options that you can use to basically clean up the spill. What you need to do is basically figure out which one is the most effective in getting rid of the nitric acid, okay? So we can look at the chemical equation, so plus H2O plus NaHCO3 and plus NaCl. Okay. Okay, and so basically what we want to figure out is which is going to neutralize it, right? Because if you spill an acid, what you want to do is you want to neutralize it. And so here we're going to have to know the solubility rules a little bit. Okay, just the important ones. Okay. Okay, so if we take a look at nitric acid and water, okay, another way that we can look at water is HOH, right? And then we can do a double replacement reaction. Okay, that's going to create HOH, right? Because these two, this will react with the anion here. And then, yeah, and then HNO3. Now, is this a reaction that's going to happen? No, because it's the same reaction, right? Same reactant, same product. There's no reaction. Okay, so this isn't going to work. The only thing it will do is it'll dilute the acid a little bit. But that's pretty much it. So probably not the best option, right? If you're slowly going to dilute it with water. 16 molar is insanely strong, concentrated. Okay, let's take a look at this now. Okay, so we're going to take a look at this. So if we react this, we're going to have H And then you're gonna have this part right here, so you'll get H2CO3. And then you can react Na with NO3. Okay, yes. Yeah, this is the anion right here. Carbonate. Bicarbonate. Okay, so if you guys take a look at it, this reaction is a bit better. The two things that we produce is we produce this compound right here, and most importantly, we produce a salt. Okay, if we produce a salt, we can see that it is being neutralized. Okay, so this right here is going to be better than the water already, because water, you're just diluting it. Here, we are neutralizing the acid by producing a salt. Okay. So far, so good? All right, now the last option right here, we are going to react the H, and it's going to react to the anion, HCl, and then you're going to have NaNO3. Now here, we have a salt, which is good. Okay, but what's the problem with the other product? Yeah, it's a strong acid. Okay, so in fact, this is actually not going to want to happen. This reaction does not want to happen because strong acids, right, they don't want to form from other acids. So this is the conjugate acid, and so this is actually not going to happen. So since it's a strong acid, the reaction doesn't really happen. Okay, so out of the three, which one do you guys think is the best way to clean up the spill? Yeah, obviously the second one. Okay, and then you can justify your answer. Very easiest way to do it is by saying that this neutralizes the reaction. That's all you need to write. Okay. Yes.
Does it matter that it's like 5%?
No. Nope.
Look at it, what they create.
Yeah, that's the best way to look at this one. What? Alrighty, guys, that's enough of the lab procedure stuff. Now we can move on to the stuff you guys love. We're gonna move on to the math part. But before we do, any questions on this section? Am I depressing you guys for the exam? Okay, there's only like one part like this, and it's shorter than this whole section. I'm doing the longer sections just so we have a little bit more exposure to it. Okay. Okay, so let's move on to the next section. Now, I want you guys, I'll give you guys about 5 minutes to do part B. Okay, this one's gonna be you're gonna be analyzing some data right here, and you're gonna be calculating for the moles of AgCl precipitate. Okay, so take about 5 minutes to try it, and then we'll go to the answer. Okay, so this part right here basically tells you what happens during the lab, all the procedures, and then you got all your data. So basically, this number right here is the alloy, basically the piece of metal that the student dissolved. And then after the student dissolved it, basically ran it through a filter, like a piece of filter paper. Okay. Now, and this is the mass of that. Okay, so basically what this tells us is that after the precipitate was formed, the precipitate is filtered. So you got your beaker, right? And then you got your filter paper, and then your solution right here went through the filter paper. Okay. The precipitate got stuck. Right, and then this is the thing that would measure the precipitate that they're finding. Okay, now key thing to note here is that it's filtered, washed, which means water went through it just to make sure that all of this solution, the stuff that we don't want, is gone, and then it was dried. Okay, so it's drying progressively, and so the first time the student weighed it, after the student thought it was dry, it was 29, this value right here. Okay, and then the same filter paper later was weighed again. So if you guys take a look at the mass changed right here, right? So what happened physically as we went from the first to the second weighing? Yeah, it's dry, it's still drying, right? Okay, so that's why there's a pretty significantly big change in the mass. And then the student weighed it again, and if you take a look at it, this is a much smaller change in mass, right? So pretty much the drying is done at this point. Pretty much done. Okay. Make sense? Okay, so if we want to find the most accurate weight of the precipitate, which one of these three values should we use? Yeah, the third one. This is the value that we want to use for the precipitate. Okay. And the key way that we know that is because it tells us that it's drying. So it's weighed first. So it's still in the process of drying as we go through this. Okay. Okay, so if we want to find the number of moles of AgCl precipitate that is collected, what we have to do is we need to do a little bit of math. So like we said, we ran it through the filter paper. And so now once we dry it completely, the only thing left is the filter paper and the precipitate. So if I want to find the precipitate, what should we do with this value right here in order to find just the precipitate? Yeah, we want to subtract the mass of the actual filter paper, right? So we're going to subtract 28.7210 grams. And that's going to give us 0.5388. 388 grams. Dang it, I can't write there. Okay, so 0.5388 grams. Okay. So far, so good. Okay, so this is the mass of the precipitate that is formed. Okay. And this is going to be grams of what chemical? What chemical is our precipitate? Yeah, AgCl. Tell us right here. Okay, so we haven't seen this in a while, but if I want to go from grams of AgCl to moles of AgCl, what value do we need to work with? Molar mass, exactly. It's been a long time since we looked at that, right? Okay, so just a refresher in case you forgot how to find molar mass. Okay, we're going to be finding the molar mass of AgCl. So we're going to go to the periodic table. We are going to take a look at Ag. So if we take a look at Ag, what's the molar mass of Ag? Yeah, 107.87. So we're going to do that. 107.87. And it's AgCl. So we're going to look at the molar mass of chlorine, which is 35.45. So 35.45. And so that's going to be our molar mass of AgCl. Okay. Added. Yeah. Okay, so since we have this as our grams, we want to get rid of grams, right? So, man, I need a little more space. Okay, we want to get rid of grams. So what we're going to do is we are going to put grams of AgCl on the bottom, moles of AgCl on the top. I'm going to put 1 mole on top because the mole or the grams of 1 mole. So this is the equation that you should have set up. Okay. Okay, so if we plug this in our calculator, 0.5388 divided by 143.32. Whoa. Okay, that's going to give us a final answer of 0.003759. If you want to change the scientific notation, that works too. 10 to the negative 3. And it's going to be moles of AgCl. Okay, so that'll be your final answer for part B. Yeah, that's totally fine too. Yeah, as long as you're in the ballpark. I do always recommend those 3 non-zero numbers after the decimal, and so, but it's not totally necessary. Yeah, the first way is fine too. Yeah. All righty. Any questions? Easy peasy. It's going. It is. All right. Okay, let's go over part C. We'll do that together and then we'll take a quick break and then we'll move on to the next section, okay? All right, last but not least, we need to find the mass percent of silver in the alloy of copper and silver, okay? So basically what we're gonna be looking at now is, let's take a look at the value we just had. So I'm gonna work with the decimal number just because it'll be easier for me to punch it in my calculator, okay? Now, what we're trying to find is how much silver was in the original alloy that we had, right? Now, we have the mass or the moles of AgCl that we just produced from that alloy. So basically, we took out all the silver from that alloy and we turned it into a salt. And so if we can figure out how much silver is in this salt, we can figure out how much silver was in the original alloy, right? Because what we did was we had the alloy, we dissolved all the silver, and then we turned it into a AgCl. And so if we can figure out how much AgCl is in the salt, we can kind of just go backwards and figure out how much was in the original alloy. That's basically how the math would work. Okay, so if we want to figure out how many moles of or how much Ag is inside of this compound right here, we're gonna have to figure out or we're gonna have to work with the mole fraction. Okay, so let's say we have 1 mole of AgCl. How many moles of Ag are in there? Yeah, 1 mole. Yeah, not trying to trick you guys. Okay, because there's 1 Ag and AgCl. Okay, now we're trying to find the mass percent, so we can find the mass of Ag. So what value would we use to find the mass of Ag? Yeah, molar mass, exactly. So we would use the molar mass of Ag, which remember is 107.87?
Yeah.
Thank you. Okay, so I'll give you guys a minute to punch that into your calculator and figure out how much or the mass of Ag that we are working with. Okay, so if you solve, excuse me, you solve that equation, you'll get something around 0.4055 grams of Ag. Okay. All right, we're not done yet. We're almost done. Okay, but if we take a look at the problem, we're looking for the mass percent in the original alloy. So what we need to do now is basically go up and find the mass of the original alloy. The alloy originally weighed 0.6489. And so what we're going to do is we're going to divide the mass of the silver by the mass of the alloy because we're looking for a percentage, right? We want to find out what percent of the original alloy was Ag, okay? And then we'll multiply that by 100%. And then we are all done. So punch that into your calculator, figure out the mass percent of Ag in the original alloy, and congrats guys, that's the end of the problem. Yeah.
Where's 0.64?
Yeah, that's the mass of the alloy because we're trying to find how much silver was in the alloy, right? So we need to find out the weight of the alloy. Yeah, good question. Okay, so you'll get a final answer about 62.49, 62.5%. That's it. So that's an example of a long answer on the AP test. There's gonna be 2 of those. Yes, 2 and then 5 shorts.
Confirm officially that you're sure, 100% sure.
Yeah,
that that's
There's always 2 long and 5 shorts.
Why can't you just use the more masses that out of like my A to B and C?
Yeah. You can do that as well. Yeah. So if that method works for you, then totally fine to do that. Yeah. There's different ways to get to the same answer. Okay, guys, we will take a quick 5-minute break if you need to run to the restroom. If you got any questions, and then we'll move on to the next one. Looking at me. All right, let's go on to number 3. Okay. So we're gonna look at an aluminum atom. Sorry, they're laughing because my voice cracked. Okay, so let's look at an aluminum atom, and we're gonna write the ground state electron configuration. So the 1s2, 2s2, that thing. So I'm gonna give you guys about a minute. This should be pretty easy. I want you guys to write the ground state electron configuration of aluminum. Aluminum. Did you know in Australia they call it aluminium?
Aluminium.
Aluminium.
How do you say vitamin?
Vitamin. They say vitamin.
Or your schedule.
What's a schedule?
Schedule.
Oh, what the heck?
When they go math.
Dude. Freaking down under.
And
Maths.
Oh, I saw. This video about.
All right, 40 more seconds to get the electron configuration. Yes, that's my name. Periodic table? Yeah, absolutely. Am I that funny to you? I don't think I'm that funny. I'm glad I can entertain you somehow. It seems like it. Dude, I bet you if I hurt my ankle here, you'd be laughing.
He fell so hard and I was laughing, scratching up, and then I was like, oh shoot, it's been like 30 seconds to get that movie, and then I stopped, okay, it was not okay.
Alrighty, guys, let's go over the electron configuration for aluminium. Alrighty. Okay, aluminium is right here on the third row. So we're gonna go through 1s2. So 1s2 because that's the front row. Okay, 2s2. Okay, 2p6. We got 3s2. And then it is 3p1. I know it's been a long time. You drew it too? Wow, extra credit. Just kidding. All right, another way you could have done it is the noble gas configuration. The closest noble gas before is neon, and then you could have just done 3s2, 3p1. Okay, either one of these is completely fine. They didn't specify, so you could have done either of those. Yeah, because of neon, the noble gas. Yes, so noble. Alrighty, make sense? All right, let us move on to the next one. Okay, so based on the principles of atomic structure, explain why the aluminium atom is larger than an aluminium ion. Okay, so I will give you guys about a minute and a half to write that explanation. It should be a very brief explanation. Okay, so take a second to do that. Let's go over this one. Okay, so if we take a look at aluminium, we look at aluminium's ground state configuration. We got three, right? We got 3 electrons in the outer energy levels. Now, if we go to aluminium ion, what happens in terms of electrons? Yeah, it loses 3, right? Yes, so we lose 3 electrons. And so if we lose 3 electrons, which electrons do we get rid of? The valence. So we get rid of these 3 right here. Okay. And so what that means is regular aluminium. Okay. Aluminium's valence shell is N equals 3, right? It's the third shell. Okay. But if you look at aluminium ion's valence shell, okay, what is the highest energy level? The N number. 2, yeah. Sorry, I thought you were saying peace to me. Yeah. So 2. Okay, which basically means, okay, I'm gonna type it now. I don't want to write it. Okay. You can just write something like when aluminium loses 3 electrons. Okay, the highest occupied energy level is N equals 2, which is a shorter distance from the nucleus. Something like that. Okay, if you were a little less technical with the language and you said shells, that's fine too.
Is he gonna like get us points taken off? Like I did not say like N equals 2, and I said like shell.
Yeah, if you say second shell, third shell, that's fine too.
Yeah, is that okay?
Yeah, that's fine.
Okay.
Yes.
I just say like as a
Yeah. Because it's talking about radius, you might want to say that it's instead of bigger, you might want to just say that it's the third shell is further away, something like that. Yeah, I know bigger kind of implies it, but again, just assume it's me, not too smart, so you gotta kind of get me through it. Yeah.
You're often saying that if you don't have the same amount of shells, you then talk about electron.
Yeah, then you will talk about electron repulsion. You will also talk about effective nuclear charge. So you want to talk about the protons as well. Yeah.
So I said it out like outside my circle, so how much you put it.
Yeah, a little bit more depth than that. Just a little.
If I like don't know what an FRQ is, I'm gonna draw a picture of you with your crutch and be like, sorry, my teacher broke his leg.
See.
He couldn't teach the rest of the year.
My teacher is special. Yes. What's up?
Like, like larger because it stays in the third cell, while the other one moves to the second cell.
You don't want to talk about staying and moving because nothing's moving or staying. You want to talk about the electrons and how many electrons it has.
I put that in this three.
Yeah, you want to say that it loses 3 electrons. So the furthest, the valence shell is now the second shell. The
So-
atom itself is not moving. You don't want to humanize. It's not a name. It's just, yeah, what we identify it as.
So when I see electron, three, so that.
Yeah, the valence shell is now the second shell, which has a shorter distance from the nucleus.
Is it better to put that in the electron? It will stay within the second cell.
You don't want to say stay.
Okay.
Yeah.
It will be within. the
Yeah,
second
you don't try not to use prepositional for
Okay.
terms. Yeah,
They may say electrons that are higher, little or farther away.
perfect.
Oh my god. I thought-
That's very concise and to the point. Great answer. Okay, let's move on to the third one. More lab stuff. Wow. Okay, so here we're gonna the student is trying to combine solid aluminum with an aqueous solution of silver ions. And then here we just need to briefly list the steps that are necessary to produce this solution right here. Okay, and then they give you some of the equipment that you can use, and it says not all equipment or lines on the table may be needed. So we went over something similar in terms of making a solution. So I'm gonna give you guys about 3 minutes. See if you guys can answer part C, and then we will move on from there. Okay. Okay, so they give you the first step for you already. You're going to use the weighing paper to measure your solid on a balance. Okay. Now you want to make a 200 milliliter solution, and if you notice, you have a 200 milliliter volumetric flask, right? And so what you're going to do is you're going to add your weighed AgNO3 into the volumetric flask. Okay, you're going to add some water. Okay, and then you're going to want to swirl. Okay, swirl to dissolve. Yeah, swirl it. You can say swirl it, dissolve it, stir it, mix it, whatever. Yeah, anything like that. Yeah, so we do need to finish filling it up, but until you want to add some water, dissolve it, and then fill it up afterwards. Yeah.
There's like no set.
Yeah, just some water. Yeah,
Why would you put it in class?
because that's where you're mixing it. Yeah, if you mix it somewhere else and transfer, you're gonna lose some of your solid, and so
Class?
yeah, the flask is really the only thing you need here. Yeah, all that other stuff is great. If you wanted to use, like, let's say, oh, you know, measure out like 100 milliliters of distilled water, pour it in, swirl it, fill it up to the line, that's fine too. But I'm just giving you the bare bones of what's necessary. Okay, next thing you're gonna want to do is you're gonna want to add, or so after the solid is dissolved, add distilled water to line. The technical term, if you want to write it, is calibration mark, but I don't even use that term. Fill water to line and mix again. Okay, and that's it. Basically, put in your solid, put some water, swirl it till it dissolves, and then add it to the line, swirl one more time to make sure there's even distribution, and then you're done. If you added more stuff to this, that's okay. This is the bare bones of what you need to get full credit. Yeah.
Require us to use all of the equipment.
Yeah.
So let's say it was like an example, someone's in the lab, or like one of these equipment, so we have to do this equipment.
Yeah, like here it says on the last sentence, not all equipment is needed, so you don't have to use all of them. You can use bare bones. If you do use more, that's totally fine. You won't get marked down for using more. You just gotta make sure you use these. And you gotta use them for these functions. Yeah. Yeah. Yeah, just make sure you mix it in the flask. Because if you do it in like a beaker and transfer, you're gonna lose some of your solid, and that's gonna change your concentration. You can use the beaker to pour in water, but graduate cylinder or volumetric flasks have a line that tells you when you're at 200, so you don't measure 200 outside. You just fill it until it gets to the line.